The purpose of this short video segment is to show you how to model a shallow truss structure on 3DEXPERIENCE release 2020x. The rationale being that we know the native FEA solver for the 3DEXPERIENCE is the old Abacus program, which is very good. And there's a lot of uh, tutorials and documentation on how to use Abacus to model structures. There are not as many in fact, there are very few when it comes to the way Abacus is embedded inside of the 3DEXPERIENCE. So with this sequence of videos, I try to alleviate that issue. Now, first of all, let me show you what the problem is. So here is a truss structure. We're assuming this is in 2 dimension and the load is applied up there. These are pin, okay, and they're all pin joints. Now, because of symmetry, we know that only half of this needs to be modeled, as you see on the right-hand side, except that obviously the load 2p, half of it is going to be imposed here. Now, this height, initial height z, and the length L, the structure is called a shallow truss because Z is much, much smaller than the length of L. Okay, that's why it's called shallow truss. Okay, now if one does a force deflection curve, the force or the load P applied versus downward displacement, you will get, or if one does this force displacement curve, we'll get something like that. And these points, this point, for example, up here, obviously this one too, but this point is called the limit point. So what that means is that as the force increases, displacement increases, and when it reaches to this point, essentially it jumps to the branch of the curve, which is on the right hand side. It's called snap through. Okay. Now, finite element packages, standard finite element packages, without doing a special, feature, which is called Rick's algorithm or arc length method, they cannot actually traverse this entire curve. So they go up to this somewhere close to the limit point and they fall apart. Now, we're going to be solving this problem, except that this particular video, this particular tutorial, I'm going to assume that there's a spring, a soft spring located here. Now, obviously, if the stiffness of the spring is 0, we are dealing with essentially the problem that I showed you. And there's going to be snap-through feature. However, with a KS here, that curve is not going to have a limit point. Essentially, it goes smoothly and it never, reverts back as you saw in the other case. So that's the problem that we're going to model. Okay. Now, under certain assumptions, small displacement, small strains, and of course elastic structure, elastic material, there is an analytical solution for this particular problem. And the data that I'm going to take is given here, okay? And this is coming from a very good video segment by this professor. And I just want to show you that with these numbers that I have here, that analytical solution that I gave you, this is going to be the force deflection curve, okay? So ultimately, when we model our structure with these dimensions and apply the load and everything, we should be able to reproduce this curve in the 3DEXPERIENCE. Okay, good. So let's go ahead and start our problem. Let me start with a part file. Okay, and create our geometry. Now, geometry, basically what I'm going to do is I will create 2 points and connect it with a line. So let's go to essentials, 2 points. First one, coordinate 0, 0, 0. Next one is going to be having the horizontal component of, next point is going to have a horizontal component, which means in the y direction of value 242499.875 and a Z value of 2025. Basically, I'm doing right here 2499.875 and the height of 25 millimeter. That will give you a length of the structure being 2500 millimeter as desired. So let me see now. View, let's fit it in. So these are the 2 points that are created. Then I'm going to create, here's 1, 0, 0, 0, and the other one is over there. And let's create our line from there to there. That's my line. Now, it is imperative that I hide these points because later on when I try to apply restraints and create a spring down below it, if I select these points where the load is applied, or restraint is applied, or the spring is created, the CAE program in 3D Experience will complain and have to fix it. So let me hide this so that I don't pick these things inadvertently. All right, good. Now, let's create our material. So let's go to View, Tools, create a material. It's a very simple tools. Where is the material? Right there. Create a material. Let's give it a shallow truss. Because I'm going to be using bar elements or truss elements, all I need is a cross-sectional area. So just keep that in mind. Right, so add a domain, make sure that your simulation is included. Very, very good. Shallow truss, okay. Now I can apply it and then make the changes here, right here. This is the one that I created. Right click, apply. When I'm done with this, I just apply it to that part. And of course, there's no data there. I go and type it in. Okay, so it is a structural problem. Obviously, abacus, mechanical, elasticity, elastic, and the value that I gave you in here, it's 500,000 Newton per millimeter squared. So I'll just type it in like that. So 500, 1, 2, 3, 4, think 5, right? So that is your 500,000, and it has to be Newton per millimeter squared. Yeah. Poisson ratio is irrelevant because link element or bar element, truss element don't need it. We just leave it the way it is. Why don't I save this thing, by the way? It's a good idea to give these proper names. Shallow truss, properties, shallow truss. Okay, and I'm going to save it. The model is pretty much done. Okay, so now we're going to go to structural model creation. I'll create an empty FEM, model and meshing, bar elements or beam elements. So I'll just use one element. So the number that I choose for the size of the element is the length of the beam. So that will give you only one element. You don't have to. It's a bar problem, link problem, truss problem, and you don't need a lot of element mesh. So right now I have only one element with 2 nodes. Okay. If you want to know how nodes and element numbers can be displayed, you can go to the tips playlist. There's a playlist that I have in my website, YouTube site, and it says tips on 3D experience, FEA 3D experience, and I show you how to activate it. I don't need it, but in case. Now we have to create the properties. Now the properties is over here 1D, and we want link. Okay, we don't want beam because this is acting as a link, as a truss. Okay, for the support, you select that line, and notice that immediately to pick the right material, and the area is cross-section area is 100 millimeters squared. Okay, good. Now we're going to create our spring element. So go to connections. Over here, this thing on the very right hand side, it says spring or rigid. I just want to spring. Now for the support, I remember I hit that those 2 points. So it's the end of this line that I'm going to be taking. Now notice that the spring goes like that. I want it to go vertical, so I rotate this thing, put the cursor there, say 90 degrees. Okay. It will rotate it once I update the mesh. And then the stiffness is you can type exactly the way it is, 1.35. I gave it in the PowerPoint. So it was Newton per millimeter, I believe. Yeah, Newton per millimeter. Now, what it does, it will convert it to kilogram per second squared. You can see that for a second. You see this? 1,350 kilogram per second square, which is pretty much that thing that I have. Now notice that it turned the spring in the vertical direction because I put a 90-degree rotation there, and good. So that's this. Okay, so let's save this, and that takes care of our basically the model, the finite element model. Okay, now we're going to go to scenario, create scenario, structure scenario creation. This is where you apply the load and restraints and eventually solve. Okay. Now you select your finite element model. There's only one that I just created. It's right there. Good. By the way, I would rather also call this thing on the properties. I'll call it shallow truss, so that when I do a search, I can find them easily if needed at any point. I don't need it in this particular tutorial, but it's a good practice. Okay. All right. Good. Okay. Now, on the procedure, we do a static analysis. If you're doing a problem which doesn't have a spring and basically it's a snap-through problem, then static analysis will take you up close to the limit point and then it stops. It doesn't converge anymore. So you have to do something else. And that's going to be one of the videos that I'm going to create later on. Okay, now, because I want to create a force deflection curve, I don't want to do it at increments of 1 second. Total time is 1. So I'm going to make it increments of 0.01. So it's gonna make 100 sub steps for display purposes right there. See that? All right. Now, incidentally, here, where was this? Right there in the step. Notice that if I do advanced, the geometric nonlinearity is included, because if I take this thing away, basically it's going to be a linear elastic problem. It's going to be a straight line. So what I'm saying is that if you take that away, basically the curve is going to go along a straight line like that. So that's okay. This is default, included by default. Good. All right. So let's go ahead and apply our restraints. So fixed displacement. These three. Move this thing out of the way. This end, not the point. Remember, I hit the point. If I put it on the point, it's going to bomb out and it's going to say you don't have proper, proper thing on the model. Okay, so X, Y, Z. You may want to try it. If you put it on that point, it's going to complain. As a matter of fact, if I have time, I'll come back and change that to that point to see that what the nature of the complaint is. And another one at this end, okay, and does not move in X, does not move in Y, but it can go up and down Z. Very good. Oh, one thing I forgot to do, that spring. Oh yeah, I did put the stiffness there. That's fine. Here, mistake. This is a mistake. This is at that point. I put it on the edge inadvertently. So let's go ahead and fix this. Under restraint, this one was wrong. See, remove it, and then zoom in. Make sure you select the end point. Now, if it's causing a problem, there's several things you can do. See, it's not letting me pick that point. Now, it is possible probably using this to pick that point. See that using this filter? Or you can hide the stuff and then pick that point. It should be that point on vertex. All right, good. Now load, force on that is, if it's giving me a hard time picking it, first of all, let me see if this solve. Yeah, this filter basically filters out everything else and lets you take that point. And the number is minus, I want to apply a force of minus 87.45 Newton, minus 87.45. And then say okay. And if you wonder where I got this thing from, oops, I think I typed in something that was not right. Let's check it out. Okay, so let's try again. Minus 87.45, and it's going to be Newton. This time it's going to work. Good. Now, if you look in the transparency here, I showed you based on this theoretical calculation, I can see that if I have a 55 millimeter displacement, downward displacement, that's achieved by a load of 87.45. So basically, I put this load there, and I want to see if Abacus will actually produce 55 millimeter downward. So I don't know 55, but I know this. I'm applying that load. That's where this is coming from. All right, so I'm going to run this and it will work. There is no problem, but I can't get the force displacement curve. So let's go ahead and actually run it. Let me see. Yep, on the simulate, I have to come back here and request information which allows me to get the force deflection curve. But right now I'm not doing it. And there is a video tutorial on how to plot force displacement curve in my tips playlist. You're going to see it again here, but that's not for a simple case. Okay. All right, so when this is over in a future video segment, I will do it without a spring. And even if I went here and made the stiffness of the spring 0, it will complain, it says 0 is not acceptable. But if you have a tiny number, it will bomb out. Okay, so this is done, no problem. And let's run it now. You will see that it'll give me a displacement of 55 millimeter, which is fine. It shows you that it's correct. However, it will not let me plot that force displacement curve because I did not ask for the proper data to be able to plot that. Okay. The derivation of that analytical formula is actually very nice. If you check that reference that I quoted on the transparency, I think you're going to enjoy it. It's not hard at all. Well, yeah. Okay, so there we are. This is the initial increment, see? And let's look at the deflection, displacement. Initial, of course, 0. So as you go further down the application of the load, this is the last load step of 87.45 Newton. Is, I have a feeling that the load, my stiffness, probably was not right, because what happens here, you can see that it is not quite, it should be 55. There's something wrong here. Let's go ahead and check it. Make sure everything's okay. So let's go ahead and check our material. There's the material. Double click on this. Yeah, this should be, let's see now. I wrote down, this is, we had to have, the conversion was not right. It's, what is that? 5, 10, 10 to the 5, okay? And then because it's per millimeter squared, this is going to be 5, 10 to the 11, 5, 10 to the 11 Newton per meter squared. So what do we have here? Oh yeah, that should be 11. Okay, let's run it again. Back to the simulation. We don't have to check the stuff because I know it's, where is this? Okay, on the simulate, I'm not going to check these things. I'm sure they're okay. I'm just going to run it. So that data that I put in there was off by 1 order magnitude. Let's see. It should give me 55 millimeter at the last step. By the way, this is real time. I'm not cutting anything from the video, so it's pretty fast. Pretty simple problem. One element, two nodes. Of course, non-linear, we know that. And I still have to go and ask for data so that I can plot the force displacement curve. So yeah, right here, 55 millimeter last step. Good. So now, how do we ask for the data? What kind of data are we asking for? So let's go ahead. Let's go back to the structure model, right there. Where is that? Sorry. Let's go back to the step here. Say we go here. Okay. Good. You see this icon here, output? You click on it. You click on it, and you ask for displacement, translation, and you ask for forces, but you want CF. Please watch that video on plotting force displacement curve, and and you're asking it at every step for entire model. Now here, there's not much, but if you have a situation where you have a lot of nodes and elements, this is ridiculous because we just want to force displacement at one point. So there are ways of doing it, but I'm asking for the entire model. So we say, okay, this is the data that you need in order to be able to plot what you want. So here, I'm not going to check these again. I'm just going to run it. Okay. It's running. These tabs are sometimes helpful. It gives you how the iterations go, etc., and how many iterations. But it's a very simple problem. Extracting results. All right, there is my 50 millimeters. So we close this, we close that, we don't need it. So now here we go, and you see down here in the post-processing basically results, there's something called XY plot from field. By the way, let me do the following. Let me hide this graph, this figure on the screen. Let me deactivate it. Okay, good. So this is on the forward mesh. Now here, XY plot from field. What do we want? We want the displacement. We want translational displacement. The support, there's the support. I want this point, this node, okay? And so there we are, translation, apply. This is the displacement versus time. And this is the dummy time, it's not real time. So it's basically displacement versus force, but I don't want to plot it like that. Now, let's do another one. So this is the first one. Let's do another one, which is not variable U translation, but it's that CF that I asked for. Apply. There is the force versus time, and I close that. Notice that I have several plots here, two plots actually, not several. One was displacement, the other one concentrated force versus time. Now here there is an icon which says XY plot from expression. You click on it. You click on f of x. See, these are the two curves that I created. Click on f of x and say combine. And these are the two curves that I created. That was the first one, displacement. That's the second one, which was the force. And then I say apply. That curve is this curve. Okay. Now, let me close this. And just to convince you that we're going to have a problem if I put those restraints and the load on a point, I'll let you do that, but I want to show you something else. If you go to the spring here, and we're going to change the stiffness of the spring. If you make it too small, essentially you're trying to make it approach zero, and it's going to bomb out. So let's make this thing, I don't know, 10 times smaller. 10 times smaller may still actually work, but we're going to see. So let's go ahead and run it. How do I go there? Okay, so let's run it. I have a feeling that, all right, this one may be big enough that it won't cause us, basically instability, but we'll see. We'll see. The good thing is that you don't have to repeat the stuff that you have already done. Once it runs, then you're going to say, okay, if it runs and it finishes, you're going to say, okay, give me the plots, okay? Because all the hard work you have already done. If it bombs out, of course, it's going to give you an error here and it won't converge. Let's look at the plot incident. Oh, this one seems to be working too. No problem. This one worked too. Didn't bomb out. Okay. Oh, of course, the displacement is going to be a lot larger. You know that because you made it less stiff. So let's look at the displacement. Yeah, instead of 55 is this. But let's go ahead and do this following. Let's go ahead and make that spring stiffness. How about 1. So that's 1,000 times smaller than what we had before. Okay, so let's go to our scenario, run it. I have a gut feeling that this is going to bomb. And by looking at the plot, by a plot I mean this, if it diverges, you'll see it. Oh, see that? I have a feeling that you see it says failed due to errors. Okay. All right. So I hope you found this video segment useful. So later on, I'm going to do one where there's no spring.